In this video, we are going to look at the fundamental theorem of arithmetic, Theorem 0.3 in our book. And it says that if you have an integer greater than 1, you can write it as a product of primes. So every integer greater than 1 is a product of primes. And furthermore, this product is unique, except possibly for the order in which the factors are written down. So, for example, if we have the number n equals 24, then we can write it as a product of primes. So what do we have in 24? We have a 2 in there, and we have another 2, and so that's 4. Then we have another 2, yep, that's 8, times 3. So we can write 24 as 2 times 2 times 2 times 3, and there is no other way of writing 24 as a product of primes other than reordering. And so that's what they mean, that we have uniqueness except for the order in which this appears. So we could write it as 2 times 3 times 2 times 2, but that's not really different. The only difference is the position of the 3 right here. So if we agree to always go from smallest to largest primes, then we can always write down this in a very unique way. So that's what the fundamental theorem of arithmetic says. And if you like, you can write down a few more prime factorizations. Just pick your favorite integer and see if you can write it as a product of primes. Now, the theorem of the proof of this theorem is very nice. There are two pieces to it. There's the existence portion, and then there's the uniqueness portion. The uniqueness portion is an exercise in the book. The existence portion we're going to talk about for a little bit. So I only want to give the idea of the existence portion of the theorem. So we are talking about how would I prove the existence portion. Okay, well, the complete proof is done by induction, in fact by strong induction. So you're using strong induction. So you have your base step and then you have your inductive step. And in the inductive step, you are supposing, so you suppose that the statement of the theorem is true for every integer up to a certain one, so up to n. So suppose all integers from 1 to n have a prime factorization. So this is our inductive hypothesis. And then now we are looking at n plus 1. So then we're looking at n plus 1. So if we're assuming that for the numbers 1 through n, no matter which one we take, we have a prime factorization, then what can we conclude about the number n plus 1? So two cases. Case 1, n plus 1 is prime. And then we are done, because there's our prime factorization. It's just n plus 1. Case 2, n plus 1 is not prime. But if n plus 1 is not prime, that means we can write n plus 1 as the product of two numbers, a and b, say, where a and b are integers between, so they are integers, and they are bigger than 2, bigger or equal to 2, and they are certainly less or equal to n. So that's somewhere between 2 and n. because n plus 1 is not prime, so we must have two proper factors. But since right here a and b is between 2 and n, and we are assuming that the statement is true for any numbers less or equal to n, any integer from 1 to n, then a and b have prime factorizations. So a and b can be written as products of primes. So let's say a is equal to p1 through pm, and b is equal to q1 through ql, and these are all primes. So the pi's and the qi's are primes. And this is true by the inductive hypothesis. So then n plus 1 was a times b, now is equal to p1 times pm, and then times q1 times ql. And here we are producing, this is the prime factorization of our number n plus 1. So we have shown that the prime factorization for n plus 1 exists. Now, just a little note right here, this was just a sketch of the proof. This was just the main idea, not the full proof. So if you want to read the full proof the way that it's nicely written down with the basis step and the inductive step and then the induction full step, please look at the notes in the workbook, and I think in the book you also have the proof of this theorem.